This video is part 4 in a series about using simple continued fractions to solve linear Diophantine equations. We'll solve a set of examples. In particular, we'll solve all 4 variants of the equation we've been using in this series. Let's get started. This is the 4-step process we already outlined for solving the equations. And this is the equation we introduced back in part 1, 101x plus or minus 27y equals plus or minus 540. We already showed how to solve one of the variants, 101x plus 27y equals 540. That was in part 3. In this video, we'll show the solutions for all 4 variants. We'll put all 4 of them on one page, including the one we already solved. Step 1 requires that we expand a over b into a simple continued fraction. A over b is 101 over 27, and when we expand it, we get 31216. We'll note that n equals 4, even though there are 5 terms, because we start counting at 0. In step 2, we consider negative 1 raised to the n plus 1 power and whether it equals the sign of the right-hand side of the equation. The sign of the right-hand side can be positive or negative, so we have 2 cases. 101x plus or minus 27y equals positive 540, and 101x plus or minus 27y equals negative 540. Negative 1 raised to the n plus 1 power equals negative 1 raised to the 4 plus 1 power, which equals negative 1. In this case here, it does not equal the sign of the right-hand side, which is positive 1. In this case, though, it does equal the sign of the right-hand side. For this case on the left, we have to convert the simple continued fraction to its longer representation. But in this case on the right, we keep using the shorter representation, which we found in step 1. The longer representation of 101 over 27 is 31251. The shorter representation is what we found in step 1. 31216. Now we're on 2 paths, and they don't merge later, so we'll put dividing lines in this box and the ones for step 3 and 4. In step 3, we calculate convergence for the simple continued fractions. Here are the tables we'll fill in. Notice that the one on the left has an extra column. And here are the convergence. These are the convergence we really care about, the second to last one in each table. These are what we need in step 4 to complete the process. In step 4, we write expressions for x and y, the integer solutions to the equations we're solving. For each equation, we'll use one of the 2 sets of generic expressions for x and y. Either this set for ax plus by equals plus or minus c, or this one for ax minus by equals plus or minus c. So we'll get 2 paths on each of the paths we already have. Over here, we get 101x plus 27y equals positive 540, and 101x minus 27y equals positive 540. And in this one, 101x plus 27y equals negative 540, and 101x minus 27y equals negative 540. What's left now is a matter of making sure you use the correct expression for x or y and finding the right values to substitute in. For this one, we use this equation for x and these convergence. We have c, which is 540, times q sub n minus 1, which is 23, minus b times t. b is 27, so it's 27t, and t is a set of all integers. Now we use this equation for y in the same convergence. We have negative c times p sub n minus 1, so that is negative 540 times 86, plus a times t. That's 101 times t. On to the next case, which has the form ax minus by, so we'll use these expressions for x and y. Notice the 2 terms in the expressions for x and y are exactly the same as what we just used in the first case. The expressions for x have a term with c times q sub n minus 1 and a term with b times t. In the first set, we took the difference between the terms, but in the second one, we add them. So now we can just write x equals 540 times 23 plus 27t instead of minus 27t. It's the same thing for y. We add the terms instead of taking the difference. Y equals positive 540 times 86 plus 101t. For the next 2 cases, the process is the same. This one has the form ax plus by, so we'll use these expressions for x and y, and we'll use these convergence. For x, we need c, it's 540, q sub n minus 1, it's 4, and b, which is 27. So we can write x equals 540 times 4 minus 27t. For y, we need c again, that's 540, and we need p sub n minus 1, that's 15, and a, which is 101. So y equals negative 540 times 15 plus 101t. For the last one, the form is ax minus by, so we use the second set of expressions for x and y, but we keep using these convergents. For both x and y, the terms are the same like we said before, but we add them instead of taking the differences. We'll just write x equals 540 times 4 plus 27t, and y equals positive 540 times 15 plus 101t. Here's what you get when you multiply all of these out. You can check them by finding some pairs of x and y and see if they satisfy the equation, or you can substitute the expressions for x and y into the equation and see if it simplifies to what is on the right-hand side. For example, you could take these expressions for x and y, substitute them into this equation, and see if it simplifies to positive 540. It does. We did this in part 3. In this video, we showed how simple continued fractions can be used to solve the variance of our linear Diophantine equation. That's all for now.